So the second speaker of this session is Najmaei, who will tell us about a type theory for comprehension categories.
Yes. So, hello. Yes, I'm Niyousha, a PhD student at École Polytechnique, and this is joint work with Benedikt Ahrens from TU Delft, Paige from Utrecht University, and Niels van der Weide from Radboud University. First, I'm going to talk about the setting we're in. So I guess we can all agree that dependent type theory serves as a foundation for proof assistance and programming languages. And we know that there are many well-established categorical semantics of it, contextual categories, categories with families, display map categories, natural models, and etc. But there is comprehension categories, which are more general than the other ones. And they are what we were going to focus on in this talk. And to motivate this, here we have a quote from Ahrens, Can you see the cursor? Ahrens, and North, which says that almost all established notions of models can be seen as sub-two categories of the two category of comprehension categories. Yes, we will see more about this later a bit also. So let's look at what happens when you interpret Martin-Löf type theory in comprehension categories. So one of the main things I want to focus on is that this semantics arrow then does not use all the features of comprehension categories. So you would have two options: either restrict your models, only focus on a class of comprehension categories and interpret Martin-Löf type theories in those, which is what usually is done, or you can try to make your type theory more expressive and see what useful stuff you would get. This is the second thing is what we do. We get to type theory by this, and we call it CCTT, which CC is for comprehension categories. Okay, so why not just restrict the models? There are two natural questions that would arise at this point. Are there interesting examples that we would miss if we do this? Or are there interesting features that you will lose in our type theory if we do this? So I will now tell you first some preliminaries, what a comprehension category is, and then we will come back to these two questions. Okay, so what is a comprehension category? It consists of a category C that you see here, a cloven fibration P that you see here, a functor chi from T to C arrow here, which makes this diagram commute. And also chi has to preserve Cartesian arrows, which I will not focus on because for the purpose of this talk it's not important for us, but this also is something that is in the definition. But something which is important for us, and I would like to point out, is when we call a comprehension category full, we say comprehension category is full if this functor chi is fully faithful, and we see that it is split if the fibration P is split. And comprehension categories which are both full and split are models for Martin-Löf type theory. So let's gain some intuition about what all this stuff that I was just saying actually is. So you can think about this category C as a category of context and context morphisms. And whenever you have a context gamma in this category, you can think about the fiber over it here as a category of types in that context. Then the reindexing functors of your fibration give you substitution. And if you have an object A, like type A here in context gamma, this chi guy here will map it to the projection from the extended context gamma.A back to the original context gamma. What about the terms of the type theory? So the terms are interpreted as sections of such projections. The terms of type A are sections of such a projection here. And this will become important in a moment. So what about vertical morphisms? These morphisms within the fibers. So if you have a fiber like this over an object gamma in C, what about these morphisms here? I did not mention them in the previous slide. So these are exactly the features of a comprehension category that at the beginning I said this semantic arrow does not touch. Yes, so these are important in the rest of this talk. But before that, back to our motivations. I mentioned it a bit before, but what I precisely mean is that a comprehension category can express both morphisms between contexts, so the morphisms here, and morphisms between types, so the morphisms here. But whenever you restrict to full comprehension categories, you are essentially killing off one of these extra dimensions of morphisms that you have. Why? Because then these morphisms between types are actually like uniquely determined. They can be recovered from the terms of the theory that you have, like from these sections of the projections I showed you before in C. And we will argue with C that that if you not kill off this extra dimension, if you keep them, then these could capture coercive subtyping for you. And back to our first question, are there interesting examples with this extra dimension of morphisms that we have? Yes, there are interesting examples. Intensional type theories, such as homotopy type theory and cubical type theory, are often interpreted in some categorical structure which are called algebraic weak factorization systems. I will not talk about them in this talk, but I will tell you that whenever you have an algebraic weak factorization system, you can get a comprehension category. And you may know that, okay, whenever you have a CWF, you can also get a comprehension category, but with these ones, the ones that arise from algebraic weak factorization systems, unlike the ones that are coming from CWFs, you would actually get a non-full comprehension category. And I can even show you what it looks like. For your category of types here, you would get the Eilenberg-Moore category of this monad R, and for your comprehension that you'll get here would be a forgetful functor. So you see that it's not a full comprehension category. And these are interesting examples that are in the literature and well studied. Yes. So I already told you an interesting feature you will lose is coercive subtyping, but what else? Maybe we have other things. So we also argue that having both terms and type morphisms could buy us a tighter control over definitional equalities. What do I mean by this? In homotopy theoretic models of Martin-Löf type theory that come from algebraic weak factorization systems, these type morphisms, these vertical morphisms that I was showing you before, they have this special, they are like special in a way, that they preserve transport of structure along the term of identity up to definitional equality. So usually this would be only up to propositional equality, but for these type morphisms are ones who preserve this up to definitional equality. And what does this mean? What does this mean? It means that you could just add such a rule to CTTT. You could add a rule that says these type morphisms commute strictly up to definitional equality with transport, and that nothing will break. Everything will still be fine. Why? Because this rule is actually validated in these models that I was talking about. And an example of this commonly used function in MLTT that it's used a lot, and you would really want it to commute up to definitional equality with transport, is the first projection of sigma types. And this is indeed for us a type morphism. So we could add this rule, and things will be fine. Okay. So now I'm done with the motivation stuff. I will now tell you what will. I'll tell you what will happen in the rest of this talk. I will tell you about CCTT, which reflects the structure of comprehension categories, and then I will tell you a bit about how it captures coercive subtyping. Here we are extending the work of Coraglia and Emmenegger. I'll also tell you about that. And then we talk a bit about type formers. So we extend CCTT in the paper with pi, sigma, and identity types. Here I will just show you sigma. Okay. So what does CCTT look like? These are our judgments. The first four should be familiar. You have seen them. It's just also, they are there also in Martin-Löf type theory. These two are not familiar. And this fifth judgment is actually corresponds to these vertical morphisms I was showing you before. So such a judgment like this is interpreted as this morphism T up here from A to B in a fiber over gamma. So we get a judgment for these vertical morphisms. And to just give you like a bit of a feel of what the structural rules look like, I'm going to show the structural rules that correspond to the category of context. But then we have similar ones for category of types and other things. So the first two rules, the first line, it corresponds to the identity and composition in the category C. And the other ones are the unital and the associativity laws in a category C. We also add, okay, then I'll not show you. You can see the rest of the rules in the paper if you want. We have rules for substitution and context extension and all the things that you might want. But we will now just go through some of them through the lens of subtyping so that I can convince you that we capture coercive subtyping. We also have this soundness theorem that every comprehension category models the rules of CCTT. Okay, so subtyping. It starts with Coraglia and Emmenegger, who were studying generalized categories with families, which is a categorical structure equivalent to comprehension categories, the general ones. And they said that these vertical morphisms there can be thought of as witnesses for coercive subtyping. And that means that whenever you see this, you saw this judgment before that we had in CCTT, you should think of it as T being a witness for A being a subtype of B in context gamma. So when we have a subtyping, I should show you a subsumption rule. And we can derive this subsumption rule in CCTT, which says if you have a witness T of type A being a subtype of type B, and also you have a term of type A, then you can get a term of type B like this, which is just the composition that you see below. And it's maybe good to note that whenever you have a witness T, the comprehension of it, so this morphism that you get here in C, is acting like a coercion function for that witness. So we also have substitution for subtyping, which looks like this, and also weakening. These are just what you would expect. So yes, I will not read the rules. It's just what you would expect, but we also have these. Okay. So now I will briefly tell you what we do when we want to extend the structural rules with type formers. So something which was important for us was that we were making a distinction between the normal, like if you just forget about the subtyping stuff and you just want to add sigma types the way you would, and then what you would need to add when you want to have all the subtyping for sigma type stuff. So when we just add the sigma types, for example, sigma types or whatever type former, I'm now going to use sigma types as an example. Naturally, we don't add rules that involve this judgment for the vertical morphisms that you saw before, and then we're going to add all the subtyping structure to it. Okay, so this is how we would add sigma types to our rules. So this is just what you would expect it to be, the formation rule, the introduction rule, elimination rule. This is just what you would expect, again, for beta and eta. And then this one is, this corresponds to a Beck-Chevalier condition. It just tells you that substitution commutes with sigma as you would expect. So we also have these Beck-Chevalier rules for Beck-Chevalier conditions. Yes. Now, what would you do when you want to add the subtyping rules, the rules for subtyping? So let's say you have a witness F for A being a subtype of A prime, and you have a witness G here for B being a subtype of B prime. Then you would expect to have such a subtyping relation between sigma AB and sigma A prime B prime, because sigma acts covariantly on both arguments. So this is exactly the rule we add, but we also expect that the coercion function attached to this witness actually acts in a certain way. So we would want it to first project the pair down, then do the coercion on the second argument, then do the coercion on the first argument, and then pair back up make the pair again. So we also add this rule that the coercion function for this subtyping relation, which was what I showed you before, the comprehension, actually does this. And we also add rules that say sigma is functorial. Yes, so this is how we get the subtyping stuff for sigma types. Okay, so this is on the CCTT side, but also on the semantic side, we have these definitions which are like what it means for a comprehension category to have subtyping for pi types, sigma types, identity types, which, so these definitions also mirror what I was showing you before on the rule side, but now these are on the semantic side. And we also have, again, soundness theorems that are like any comprehension category with subtyping for sigma types models CCTT extended with subtyping for sigma types, also for pi and ID. Yes. Okay. So I will now close with some related work. So there has been a lot of work on subsumptive and coercive subtyping and their semantics. So Salberger and Méliès give a Fabrician view of subsumptive subtyping as opposed to coercive subtyping that we study. And Coraglia and Emmenegger, they, as I told you, they were first observing that these type morphisms can be witnesses for coercive subtyping, but in generalized categories with families. Laurent, Lennon, Bertrand, and Maillard, they extend Martin-Löf type theory to a type theory with that has definitionally factorial type formers, and then they use this to extend Martin-Löf type theory to a type theory with coercive, and then another one with subsumptive subtyping. See, I cannot pronounce it. This is why we're doing coercive subtyping. Yes. So there's a close relation between our work and their version of their type theory with the coercive subtyping. Then Adjudge, Benjamin, Lennon, Bertrand, and Maillard, they develop a type theory which is model-wise split generalized categories with families which are equivalent to split comprehension categories, and then they also provide a general framework for defining type formers that are automatically functorial. This is also POPL this year, so we are also closely related to them, our work. Yes, I think this is all I wanted to say. We design CCTT, it reflects comprehension categories, structure of comprehension categories, and then we say if we don't kill off this extra dimension, then we get coercive subtyping. Thank you.
Lovely talk. Thanks for the
Yes,
talk. I finally understand comprehension categories a bit better. I was wondering whether you looked at algorithmic aspects of these type theories.
Yes, we did not. But yes.
Okay.
Yes, thank you.
Yes. So thank you for your talk. So so you described in slide 19 how sums work. Yes.
Yes.
Sigma. Yes. Sigma
yes.
types. So
you want me
so
to
I guess you. Yeah. I think it's good. You can come back to it. So do you have something similar for
here?
Yes.
Yes.
And so something for pi types, because pi types are very interesting and surprisingly they are connected to linear logic. So I was wondering whether you noticed that.
Yes, we have. It's similar, but here it's just, for this page, the difference would be this part. So it's just contravariant, but then the rest is the same. We also have the comprehension category with pi types.
Okay, but there is a subtlety about the way, I mean, yeah, okay. In fact, what happens is that the type that you get is exactly the type that you would get for implication, but contravariantly in linear logic, like as a negation of the tensor. And I wonder whether you observed that in your work.
Yes, we did not like, we were not looking for it,
yes.
But I think you would still observe.
Okay,
maybe
okay.
we can.
Because I think it's quite a beautiful thing that, you know, at the heart of dependent types, we have something coming from basic ideas of continuations. Yeah.
Yes, we can discuss
later.
later.
You saw that, okay, good.
Yes. Thank you.
Hi, thank you for the talk. You had soundness results. I was wondering, what are the obstacles for completeness?
Completeness?
Yeah.
Yes. So we discuss a bit how we would go about, how we would proceed for a completeness proof. I guess we have just not done it because it was kind of out of scope for us. But we give like a sketch of how you would do it, and which it would be similar to like which other related work we have done it.
Okay, thank you.
Yes. Yes. No questions?
Any other question? So I had one. At the beginning, you said that you gave as a motivation this example of algebraic weak factorization system for non-full comprehension categories.
Yes. Here.
Of course, I immediately see that it is not full, but do you have a slightly more explicit example that I could like squeeze out and concretely observe?
Yes. So there is one. Okay, I will tell you one now. So imagine you can work it out, and in the end you would end up with this. So this category C here would be the category of groupoids. Okay. Then the C arrow would be like all the groupoid functors of them, and then the morphisms would also be like these commuting squares. But then you see that EMR is then groupoid functors that are equipped with the structure of an isocleaving. So the morphisms here then would be only the ones that strictly, like on the nose, preserve this isocleaving structure. So then this also then forgets all of these for you. Yes, this is one. You can also do it with cubical sets and like, yes, cubical sets, and then the category of types would be cubical sets equipped with a fibrancy structure.
Okay, thanks.
Yes.
So if we don't have any other question, let's thank the speaker.